Hi, so in a previous video called, I think it was Easy, Fun, Powerful Battery to Make at Home, we made a battery that was activated with ordinary vinegar and table salt. And somebody asked, would it work with ordinary table salt? Well, of course, the first thing you need to do in a question like that is test it. So what I've got here is a bit of zinc, and I've got some table salt in some water here, and I've cut off a piece of Oasis floral foam, wet it in the salt water, pop it on the zinc, and we used a piece of carbon, and here's my bit of carbon. This is actually a carbon felt. I use this because it's really convenient. You can find it in things like air filters, that sort of stuff, but you can use activated carbon as well. We pop that on, and then I've got the other side attached to a stainless steel current collector, and here's my motor. Now if I touch those two together, we should expect something, and what we're getting is nothing. Well, that's not really a surprise. The zinc is coated with a zinc oxide. You can't really see it, but it's there. If you were to sand that off, you would in fact get it to work. And we can try that with a piece of sandpaper. So all we've done now is remove that oxide coat. That back on, there's my salt-soaked piece, and there's my stainless steel current collector. And now the motor's working. And the motor's working because we got rid of the zinc oxide layer. And that's what the vinegar does. The vinegar attacks that oxide layer, gets rid of it, and then the zinc can actually react. But of course, it will only react until an oxide layer reforms. It's called passivation. And the acid that we used, because vinegar, remember, is acetic acid, depacifies the surface, or if you like, depolarizes it. Now, it's unfortunate really that zinc does that, and the next question I was asked was, what other metals could you use? Well, you can't use copper. Copper just isn't reactive enough. And we have here a piece of copper, and we can do exactly the same thing, and of course get nothing at all. Even if we remove the oxide coating on that with a piece of sandpaper, we still got nothing. So the material, the metal, has to be reactive enough. And if you have a look on the Reactivity Series, it'll tell you what kinds of metal are going to be reactive enough. Now, it's possible for a metal to be too reactive, because remember, you want a controlled reaction so we can get that power out nice and evenly. If it reacts too violently, all that's going to happen is the thing's going to bubble and you're going to have a mess on your hands. Now, if you have a look at that Reactivity Series, then you'll see this metal placed really rather nicely. This is a piece of magnesium. Now, it's again relatively easy to get hold of magnesium. This stuff is printer's plate actually, so if you're having printing done, or if you're having hot foil or something like that, they use big thick blocks of this stuff. It's also the stuff that you find in fire starters. That's magnesium as well. And if we pop that on with the magnesium, and here again, this time I'm going to remove the carbon, and we'll see that work. And there we go, it's working. Now the problem with it is, although it works, it doesn't work particularly well. So right here I've got another carbon, but this carbon has a special treatment on it. And if I put the special treatment on it, you really get an awful lot more energy. Now I'm going to give you a better close-up of that so you get a good idea of the difference between the magnesium all by itself and the magnesium with the specially treated carbon. So here is my piece of magnesium, here is my table salt water floral foam, and I pop the stainless steel current collector. There you go, turning. Now I've got my special carbon. See the difference in the power there? Okay, so really quite an impressive difference for laying on this bit of carbon. And of course the immediate question is, what is that special treatment? And I'm about to tell you. These are metal air batteries. They in fact work because the metal is rusting in a controlled way with the oxygen in the air. Now it will do that all by itself. Iron does that if you just leave it lying outside. It's just very, very slow. Here we're increasing it, and we're increasing it by using a catalyst. And this piece of carbon has been coated with the catalyst. Now there's a whole lot of catalysts you can use, and if money is no object, then platinum does really, really well. But for most of us, money is a real object, and what we need is a catalyst that is easy to apply and really quite cheap. And there is one. The catalyst on here is in fact manganese dioxide. Now the manganese dioxide has a nanoparticle form, but the nanoparticles are incredibly easy to make. All we actually need is some ordinary water and some of this stuff, which is potassium permanganate. Now I have quite a lot of this obviously because I'm a research lab, but you can buy this in the chemist in 2 or 3 gram lots very, very easily, and the amount you need is absolutely tiny. So we've got here about 150 to 200 millilitres of water, and we need about that much. It's about 0.1 of a gram. It's a tiny, tiny amount that you need. And you pop that in there, and that will go the beautiful bright purple colour that we know manganese dioxide, potassium permanganate to be. So it's this beautiful purple colour. You use this actually as a topical antiseptic, which is why you can get it from the chemists. But potassium permanganate has a very curious property. Again, if we take a bit of this carbon felt, and again you can do this with any activated carbon, the potassium permanganate will attack the surface of the activated carbon. So we pop our felt in there and make sure it's covered. Now it won't do it at room temperature. It has to be somewhere between about 60 to 90 degrees centigrade, and you stir that at 60 to 90 degrees centigrade for about 2 hours. That potassium permanganate will be adsorbed onto the surface of the carbon, attack it, and break down to nanoparticles of manganese dioxide. If you make this too strong, you'll get particles of manganese dioxide and they won't work. You need nanoparticles, and you control the size of the nanoparticles by concentration. So these are very weak solutions. You want them in the order of 0.05 to 0.01 molar concentrations. And stir that, that will actually just go clear. It'll go clear and you'll see your felt inside. Get your felt out, give it a wash and dry it, and you'll end up with something that looks identical to what you started with. They look no different at all. But this one will have the manganese dioxide nanoparticles on it. Now, manganese dioxide nanoparticles on carbon are catalytic for something called the oxygen reduction reaction. And that is where we get that extra power from. This is allowing the oxygen to filter into the carbon, react with the material in the electrolyte, and attack the surface of the magnesium, turning it into magnesium oxide. So we are rusting the magnesium in a very controlled way using a nanoparticulate catalyst that is extremely cheap and easy to make. And gives awesome results. This will last until the magnesium is eaten away. It's about 1.85 volts that you get from it. It'll last for as long as the magnesium lasts. When you need to charge it again, then you put more magnesium in there because you are using a catalyst. The good thing about this, obviously, if it's in a dry form, so we now have a dry bit of Oasis and a dry bit of our catalyst, then we pop them on there and there, and we get absolutely nothing, which is awesome because that will last forever. And then all we actually need to do to get this thing going is take some ordinary salt water and wet that Oasis. And there we go. Isn't that amazing? Anyway, I thought I would share that all with you because I thought it was interesting. I hope you enjoyed the video, and thank you very much for watching.